right. So, we've been talking about repeated games, and we're at this sort of interesting transition point in the term where after today, you're all really going to be familiar with the concepts of game theory. We've got our basic matrix form game down, we've got our extended form games, now we've got this concept of what happens when we play games over and over again. So starting next week and moving to the end of the term, we get to talk more about things like applications rather than theory. So I think this is really cool because what we're aiming to today is just finish up the theory of game theory. So to be clear, last time what we did is we introduced repeated games as a concept. There are two types of repeated games. Finitely repeated, so games that we only play a set number of times, and infinitely repeated games where repetition can go on forever. And note, I say can in the sense of going on forever is possible, but in practice, the way we think about repeated games is not that they're going on forever and ever and ever, but more that we don't know what that endpoint is. So we gave examples. A finite game might be you all coming to Sweetbriar. Eventually, you're going to leave Sweetbriar. Whereas an infinite game might be how you behave in your day-to-day life. So certainly you're not going to live forever. But you don't know exactly when you're going to die, and so you have to model it like it's an infinite game. Sweetbriar, on the other hand, you have a pretty good sense of when your Sweetbriar career will be over. And so you can model your Sweetbriar career, this finitely repeated game. You're just taking a bunch of classes until you graduate. You can model this finitely repeated game as a sequential game. First is your freshman year, sophomore year, junior, senior, and then you graduate. And because we can model finitely repeated games basically just as a sequential game, we can solve using backwards induction. So at the risk of abusing this metaphor too much, you all knowing what you want to do after you graduate or not knowing can help you decide how to behave in your Sweetbriar career. Which professors are you going to need recommendation letters from? Given that, which classes should you try really hard in? Which classes can you blow off a little bit? We can think ahead to where we want to be at the end of our Sweetbriar career and backwardly induce how we should behave now. Today, what we're going to be discussing is Equilibria in infinitely repeated games. And this concept of infinity can seem scary. Infinity can seem like a scary concept. It's calc-based math that we don't need for this class. It's not a number so much as a series of numbers. But as we talked about already, we're just using infinity to stand in for something that we're already familiar with, which is just unknown, indeterminate endings. We're not going to live forever, but our life is an infinitely repeated game because we don't know when our life is going to end. We can think about this a lot of ways. In business, we don't know when our businesses are going to close down, so we treat them as infinitely repeated games. And as it turns out, we're actually already quite familiar with a strong concept in infinite repetition. Does anyone know what it is, what I'm hinting at? Does anyone have any questions before we move on? So we're already quite familiar with the concept in one form of infinite equilibrium, and that's mixed strategies. What do I mean by this? Because we spoke about mixed strategies really as a sort of static concept. But remember, a mixed strategy is just a probability distribution over the set of possible outcomes, possible actions. And in a mixed strategy, as opposed to a determinant strategy or a pure strategy, in a mixed strategy, we're trying to maximize expected payoff rather than realized payoff. And statistically speaking, this concept of expectation has infinite constructs embedded to it. Right? If we played a game an infinite number of times with our mixed strategy, what would our average or expected payoff be? And when we talked about expected payoffs in the more static sense, we split the number of actions into this finite number, but we can think of expectation over an infinite sum. So whereas last time we talked about it in just terms of simple arithmetic, expectation is weighted value, probability 1 times outcome 1 plus probability 1 or probability 2 times outcome 2, we can generalize that to a more infinite form. And it's fine if you're not comfortable with this math notation. What I want you guys to be comfortable with is the broader concept that we're already used to dealing with infinite forms. Questions so far? So let's quickly review what our mixed strategies look like. And remember, we had this very simple way of talking about mixed strategies, this very compelling way of talking about mixed strategies, which is you deciding whether or not to drive drunk, and the police deciding whether or not to set up a checkpoint. So Julia, are you slipping anything into that bubble tea this weekend?
No.
All right. You're going to be in this cell, right? So remember, we have this concept of you deciding whether or not to drive drunk and the police deciding whether or not to set up a checkpoint. We had some assumptions behind this game. Drinking wine is more fun than drinking bubble tea. Drunk driving is costly for everyone. It's bad for the city. It's bad for you. It's bad for you if you get caught. It's bad for the city if you don't get caught. Setting up checkpoints is costly for the police. So we have a bunch of uncertain outcomes, and we want to come up with a mixed strategy equilibrium here. Now we're going to go through this relatively quickly because you should already be familiar with the mixed strategy. We're just using it to introduce our broader concept of infinitely repeated games. So remember, a mixed strategy equilibrium is an equilibrium where every action played with positive probability must be a best response to the mixed strategy played by others. This means we want to set up indifference conditions. So if the police are setting up checkpoints with probability Q, we want you to be indifferent between drinking or not drinking. If you are drinking with probability P, we want the police to be indifferent between setting up checkpoints or not. Every action must be a best response. And for it to be a best response, we have to be indifferent. Because otherwise, if we weren't indifferent, we would have a preferred outcome. And so we can't be in a best response. So how do we set this up? How do we solve for this mixed strategy equilibrium? How do we solve for it? This is all review at this point.
So we would do, it would be the negative 2, 2, and then would be 3 minus 6.
You tell me. If the police are setting up checkpoints with probability Q, what's the probability they don't set up checkpoints?
It would be
Don't set up the whole problem. Just answer this. If the police are setting up checkpoints with probability Q, what's the probability they don't set up checkpoints?
1 minus Q.
1 minus Q. All probabilities must sum up to 1. You can't have a probability that's more than 1. You can't have a probability that's less than 0. Okay? So minus 2, that's our payoff for drinking wine and getting caught. That happens with probability Q. plus 1 minus q, what's our payoff there?
1.
1. That's our probability. That's our payoff for drinking wine and not getting caught. Anything times 1, the 1 just drops out. We're setting up an indifference condition. But the cool thing here is we don't get any payoff for drinking soda. So our indifference condition is 0. From here, we can move this 2q over to this side. So 1 minus q equals 2q. 1 equals 3q. I just moved the q over. Q equals 1 over 3. And I'll put a star there, Q star, because this is the optimal mixed strategy for the police in terms of setting up checkpoints. All we did was figure out an indifference condition. The police are at a mixed strategy equilibrium if your actions are a best response to their probability distribution. That's how we get this indifference condition. You are indifferent between drinking wine and not if they are setting up checkpoints optimally. Their optimal probability for setting up checkpoints is 1/3. So they set up checkpoints 1/3 of the time. Already, even though we're familiar with mixed strategy equilibria, when we say 1/3 of the time, it has that feel of infinite, right? And we don't know how long we're going to live in this city. But every time we go out, we can think that the police are setting up checkpoints 1/3 of the time. It's sort of a repeated game, an infinitely repeated game. Let's, just to keep the review going, solve for P. How do we do that?
You do the same thing, but with the police.
Great job. We set up an indifference condition. So you're drinking wine with probability P. What's the police payoff for you drinking wine with probability P? What's the police payoff for checking, I should say?
Negative P.
Plus?
Plus negative 2, 1 minus P.
So, not quite. This is their expected payoff for checking. So you're drinking with probability P. We want negative P minus 1 minus P. We want the police to be indifferent between checking and not checking. So that's their expected payoff from checking. You see how we got that? You're drinking wine with probability P. You're not drinking with probability 1 minus P. It costs them 1 to set up a checkpoint. There's no cost to society for your drunk driving because you get caught at the checkpoint. So it's -1 in both circumstances. We'll note that that simplifies to -1. -1 here and -1 here. Just like you drinking soda, your expected payoff was 0. This is an indifference condition. We want the police to be indifferent between checking and not checking. What's their expected payoff for checking?
Is it just -1?
Or, sorry, not checking. We just solved for their expected payoff for checking. -1. What's their expected payoff for not checking? Well, you're drinking wine with probability P. What happens to the police if you drink wine and they don't check?
-2.
-2 times probability P. And what happens to the police if they don't check and you drink soda?
Nothing.
Okay? So -2P equals -1. That's our indifference condition. We can simplify that to 2P equals 1. And P star, because this is an optimality constraint, equals 1/2. We want to calculate expected utility in each circumstance. So what's your expected utility of drinking wine relative to soda? 1 minus 3q equals 0. Q star equals 1/3. That looks like what we got here. What's their expected utility for you drinking probability P? Minus 1 equals minus 2p. That's what we got up here. For P star equals 1/2. Questions so far? When we were talking about mixed strategies, we also noted that since there's no pure strategy equilibrium, this is the unique Nash equilibrium. The mixed strategy equilibrium is the unique Nash equilibrium, which starts to make sense when we think about this as a repeated game. Because we're doing this over and over again, and if everyone was doing the same thing every time, rather than choosing from a probability distribution, the world would be really static. It wouldn't have that dynamic flair to it. We would already know what to do. Whether to drink and drive, or drink soda, or set up a checkpoint, or not. Mixed strategy equilibria are a really great way of thinking about infinity, and a really safe way of thinking about infinity. Infinity is a scary concept. But rolling dice, doing things probabilistically, is something we're much more familiar with. Yet this probability has an infinity embedded into it. There are other equilibrium concepts. There's the Folk theorem that we discussed last class, and then there are specific equilibrium strategies. And like I said at the beginning of class, this is not a calc class. The way these theorems are derived is by using calculus. We are going to skip past that and talk more about the concepts behind them. So remember, the Folk theorem basically says that we can get out of the prisoner's dilemma, and it doesn't have to be a prisoner's dilemma, but it basically says that under the right conditions, we can find an equilibrium if the game is repeated enough times, and by enough we mean infinity, and our discount rate is low enough. Remember, we talked about this last class. Future money is different than money now. Future payoffs are different than the payoffs we get today. We're not going to talk about discounting beyond that, but conceptually, it makes sense that we would think about, in a repeated game, and in an infinitely repeated game, what happens 10, 20, 30 years down the road is being fundamentally different. So depending on how we value the future, with enough repetition, we can come up with, let's call them cooperative solutions to games. Questions so far? So one of the areas in which game theory has a lot of strong applications is in industrial organization, how firms interact with one another. Remember, game theory is just strategic behavior. It's when your choices, your actions, influence the payoffs of others and vice versa. So this happens with firms. Firms are interacting with one another in a marketplace. And the price that one firm charges, the price that Wegmans charges, is going to influence how much money Food Lion is making. So first, let's think about this pricing problem. Are there any pure strategy equilibria? Let's put it differently. Are there any dominant strategies in this pricing equilibrium, in this pricing game?
To charge the low price.
Charge a low price. Let's do it together as a class. If firm 2 is charging the low price and you're firm 1, and Jade, let's run with it. Let's call it Wegmans and Food Lion. If Food Lion is charging low prices, what do you want to do as Wegmans?
Do lower prices.
Do lower prices. Because if you're Wegmans and you're charging a high price, and Food Lion is charging a low price, everyone's going to go to Food Lion. Corn is corn. Bread is bread. When one firm is charging a low price, the other firm wants to charge a low price. What if Food Lion decides to charge a high price? What does Wegmans want to do?
A low price.
Food Lion is charging the high price. Wegmans still wants to charge a low price. Low pricing is a dominant strategy here in the one-shot static game. Because if they're charging a high price, you can steal all their customers. No one wants to go to the expensive grocery store when there's a cheap grocery store in a world where all grocery stores are the same. We see the same thing in Food Lion's reaction to Wegmans. Low pricing is a dominant strategy in this case, which means both firms charging a low price is a Nash equilibrium. This looks a lot like a prisoner's dilemma, where there's a dominant strategy resulting in an equilibrium outcome, but this equilibrium outcome seems kind of inefficient, at least to the eyes of the grocery stores. All of us, the consumers, might benefit from them charging a low price. But if you're Wegmans, do you want to be earning $10 a week? No, you'd rather be earning $50 or $100, if possible. Now, low, 10-10 is the equilibrium outcome in the static, simultaneous, one-shot game. But we're not in that world anymore. We're in the repeated game. And you, the new CEO of Wegmans, has to live in a world, day after day after day, where you're competing with Food Lion. So maybe there's a way where you and Food Lion can both get $50 a week instead of $10 a week. Questions so far? Suppose the game is repeated over and over again. For instance, suppose Wegmans and Food Lion announce their prices simultaneously on the first day of every month. Every single month, from now until they both go out of business. Do you want to play anything differently? And think back to what we were doing in class on Monday when you were playing repeated games.
Is there any communication?
There's no communication, but, first of all, that would be illegal. Firms are not allowed to collude on pricing. But what is perfectly legal is what we do anyway, which is we know what they did last week. I'm not calling up the CEO of Food Lion and saying, let's cut costs on corn, but I do know what you did last week. And this is what we did in class on Monday when you guys were playing games with one another and you were repeating them. So who remembers some strategies that came to bear when we were repeating games? And when we were repeating them, we'll say infinitely, but what it means is you all, as players in the game, didn't know the end point.
Adapting to the other person's choice.
Okay, so I remember in U2, one of the things you did was, Julia, I believe you just did whatever it was that Jade did last time. Jamisha, did you do anything different when you were playing with Grace?
Oh, we took turns, like for the jam on Courthouse, and then for the other one, we ended up, like after 3 turns, we ended up just picking the same place.
All right. So one of the ways we can think about this strategy is what's called tit for tat. And in a repeated game, a tit for tat strategy is where one player responds in kind to the opponent's previous play. Julia, this is basically what you did on Monday. You took whatever Jade did last time and gave that answer. What this means is that in the condition where Jade is cooperative, in the condition where Wegmans is charging a high price, Food Lion also charges a high price. If Wegmans ever betrays you and charges a low price, then Food Lion is charging the low price. We are no longer in this static, simultaneous one-shot game. We're now in a repeated game. So, as the grocery store is in question, what do you want to earn each week? Do you want to earn $50 or do you want to earn $10? 50. 50 is more than 10. So Jade, suppose Julia has decided to match you and charge $50 or charge a high price with you so you're both earning $50 a week. Are you gonna undercut Julia and charge the low price so you can earn $100?
Yeah, probably.
Maybe in the one-shot version, but what happens then? Now that we're repeating this game.
And Julie also wants to go down.
Yeah. So in a one-shot version, if you had a magical time machine where you could switch your decision, you would want to switch because 100 is more than 50. But in a repeated version, and in particular in an infinitely repeated version, you know that Julia is just going to match you. So yeah, that $100 next week might be fun, but from there you're going down to 10. You know Julia's going to charge the low price if you do it. And it's worse, because now that you know that Julia's charging the low price, can you go back to the high one? So suppose you know that Julia's charging the low price. If you go back to high price, you're losing $50, and she's making $100. Questions so far? Because this is no longer a static game, because this is no longer a one-shot game, when you are playing the game infinitely many times, cooperative behavior can be sustaining. Assuming you know that Julia is playing this tit-for-tat strategy. You know that whatever you do, she's going to match. If you guys are at this cooperative equilibrium, where you're both earning $50 a week, you don't want to deviate from that plan, because yeah, $100 might be fun next week, but you're not staying at $100 forever. And the expected gains, remember, we're in an infinite world, we're talking about expected value. The expected gains from cooperation will outweigh the expected gains from undercutting. Even though you'll get a small boost in undercutting. You'll get $100 for 1 week, but no weeks after that. Questions so far? Let's go back to what we were talking about on Monday a little bit. How come this doesn't happen when the game is finite?
Because you use backward induction. And then
Yeah, we'll use backwards induction, but the thing that makes that backward induction work is you have no incentive to cooperate in the last round. That's what we're inducing backwards. You have no incentive to cooperate in the last round. Why does cooperation work? Because in an infinitely repeated game, there's always a next round. So under finite repetitions, firm 2 or firm 1 or Wegmans or Food Lion or however you want to think about it, aren't going to think about undercutting until the last month. But once you think ahead to the last month, it's important to consider the second to last month and the third to last month. In the finite game, we can induce backwardsly, reverse induce, to get us to charging the low price every time, that inefficient prisoner's dilemma equilibrium. And this doesn't happen in an infinite game. Questions so far? So remember, what we want to do with these infinitely repeated games is think much more through applications rather than concepts. So what does the tit-for-tat strategy look like in practice? It looks quite successful in practice. And there's a couple of reasons why. One is we don't know when the game ends. We've been calling it infinity. We've been calling it sufficiently large n. But that's not what we mean. We just mean indeterminate ending. Wegmans will eventually go out of business. Food Lion will eventually go out of business. But those considerations aren't going into how they price their corn right now. The considerations about how they're pricing their corn right now are, what did Wegmans do last month? And what's Wegmans going to do next month? And Julia, to your question earlier, they can consider this without talking to the competitor. What Wegmans did last month is a matter of public record. Even if you doubt what they're going to do, what strategy they're going to play, there are benefits to playing the tit-for-tat strategy cooperatively. You can always go back to that inefficient equilibrium, that low outcome where you're only earning $10 a week. So why does tit-for-tat work in practice? This possibility, just the fact that there is a possibility, can make cooperative behavior seem viable. We know that future money isn't worth as much as money now. But with a sufficiently long time horizon, it's going to be more profitable, it's going to be more beneficial to us to cooperate. Now we'll note that cooperation can break down for a lot of reasons. Because what we're doing in game theory is abstracting reality. There are more players in the marketplace than just Wegmans and Food Lion. There are ways in which Wegmans is differentiated from Food Lion beyond price. Quality, cleanliness, fantastic cashiers. There are legal reasons why you might not want to seem cooperative. Even if you are not colluding, you don't want the impression of collusion. Demand can change, so maybe our game looks different. Even the matrix form of that game might look different next month than it looks now. Cooperation can break down. But playing this game repeatedly with a competitor it is possible for two perfectly rational competitors to behave cooperatively in a way that we don't see in the static one-shot version. Questions so far? All right, so let's do a couple examples and then we'll move on to Grim Trigger. water meters. For the last 4 decades, give or take, almost all the water meters are the things attached to your house or apartment building that say how much water you're using. Almost all the water meters have been produced by 4 different companies: Rockwell, Badger, Neptune, and Hershey. The people who are buying the water meters are the water companies. Funny how in my 170 class this morning we were also talking about water companies, but in completely different contexts. The people who are buying meters are the companies, the utilities themselves. Why? Because they want to know how much they can charge you for taking a hot shower. Water is a good in econ that has relatively inelastic demand. Inelastic is a stupid word that economists use, but it just means sensitivity. Water is something you need. You need to drink, you need to shower, you need to wash your hands. You're always going to need water. Which means when the price changes, you don't change your consumption that much. Because you still need to drink, wash your hands, and take a shower, even when the price of water goes up. Demand for water is both inelastic and stable. It's also hard for new utilities to enter the marketplace. Water and utilities more generally have high fixed costs. I can't just start a water company right now to compete with Rockwell, or the municipal utility, I should say. So we have a situation where water utilities seem like they could earn lots of profits if they were cooperating. So we've got this firm, or set of firms, facing a prisoner's dilemma. They've got a situation where they would earn a lot more money if they behaved cooperatively, but it's also probably a dominant strategy in the one-shot setting to undercut and behave aggressively. So what happens in the market for water meters? Do Rockwell, Badger, and Neptune compete, or do they cooperate?
I have a question. It's not bad. But don't they usually split the area to where the company can provide service? You don't actually get to choose.
Yeah, so it's a little confusing, this example, because we're not talking about the utilities. We're talking about the people who are selling water meters to the utilities. So, because you always need water, the water companies always need to buy meters to monitor you. So we're talking about not City of Lynchburg Waterworks. We're talking about who they're buying their meters from. Excellent question. But with that in mind, we have 4 firms in this industry: Rockwell, Neptune, Hershey, and Badger. One of them can undercut the others, behaving aggressively, cutting everyone's profits, or they can behave cooperatively and charge monopoly prices. So what's going to happen?
With this being like an infinite game, because they don't know when it will end, wouldn't it be more beneficial in the long run if they just were cooperative?
Okay, so we think there might be cooperative pricing in the long run because they're always going to be selling water meters. Anyone think differently?
Yeah, because I remember you saying I guess that's the game changer where if you betray me once, I'll never trust you again. So if they undercut them now, then they'll all go to that price as well.
Yeah, this has been historically a very cooperative industry. And remember, we're talking about the people making the meters, not the utilities themselves. There have been, over the last 40 years, very few attempts to undercut the price of a water meter. And the firms have generally been satisfied with their market share. But, like you said, we don't know when this game is going to end. It's infinitely repeated in the sense of indeterminate endings. And the water meters attached that your parents are used to are not what water meters look like anymore. Now there's a big push in the industry to have smart meters. And the fact that there's now this big push to have smart meters means we're going to see new entry into this marketplace, much more competitive pricing. We're moving out of this oligopoly and into what looks like a more competitive industry. To put it in terms of game theory, this game, which has been going on repeatedly for the last 40 years or so, looks like it's coming to an end because the industry is shifting. Smart meters, unrelated to that, are actually super cool. You guys should look them up. Questions so far? Airlines. In March of 1983, American Airlines proposed that all airlines adopt a uniform fare schedule based on mileage. So flying Delta from Atlanta to New York would cost about the same as flying American from Atlanta to New York. Most of the major airlines reacted favorably to this proposal. Now, is the reason they reacted favorably because they were worried that their consumers were confused by the different pricing models out there? No. They want to reduce competition and collude. They want to screw you guys over. Prices have been driven down over the last several years by competitive pricing strategies, by undercutting airlines as they compete for market share. The problem was airlines are going bankrupt. In the competitive prisoner's dilemma, each airline, American, United, Delta, has incentive to lower fares in order to capture passengers from its competitors. Air travel has very unpredictable demand. None of us have been on a plane in a while. 2 years ago, we couldn't have predicted that. So aggressive competition always hurts the airline industry. Those of you who are on the business side of things, remember this lecture because airline strategy is actually quite interesting. Strategy in the business sense is basically just applied game theory. But we can think about airlines competing on a bunch of different things. We can think about them competing on price, like Southwest does. We can think about them competing in service, like United does. We can think about them trying to compete on both, like JetBlue tried to do and failed miserably. What we have is a sort of split level in the airline industry, where we've got 3 airlines, Delta, United, American, that compete on loyalty. And they charge roughly the same prices for a flight from Atlanta to New York. And then we've got this other level of airlines competing on price, where we've got Southwest really wanting to undercut the price of all their competitors. But if you're flying Southwest, you don't go Atlanta to New York, you puddle jump. Delta, American, and United have a hub and spoke model, where there's a couple airports, should be familiar to all of you, O'Hare, major United hub, also an American hub, Atlanta, major Delta hub. You're from Charlottesville, but let's say Dulles, also a United hub, also a Frontier hub. Hub and spoke model, because they have to price differently than Southwest, has a hop-to-hop-to-hop model. Questions so far? All right, so let's close the day like I said, I think we can end pretty quickly today by talking about Grim Trigger. Grim Trigger is a particular kind of infinitely repeated game strategy where, unlike tit for tat, in tit for tat, you do whatever your opponent did last time. And with the right discount factor, with the right numbers, you can revive competitive behavior. So in that example with Wegmans and Food Lion, you didn't have incentive as Food Lion or Wegmans to undercut pricing. But if you did, in tit for tat, because they're doing whatever you did last time, you could get back to that cooperative equilibrium, even if you temporarily leave it. Grim Trigger, you can't. Grim Trigger means if you defect on me, if you cheat on me, I will never trust you again, and it's going to screw both of us over forever. As soon as the opponent defects, this is the trigger condition, the player using a Grim Trigger strategy will defect for the remainder of the game and never come back. Let's talk about what this looks like in Prisoner's Dilemma, and then we'll bring it, yeah.
Can you go back?
I'm not going to go back just because it's recording right now and that screws up the recording, but I can read to you, and the slides are posted. What is it that you need to copy down?
I just had lessons. It's okay, I'll get it.
Okay. All you need to know about Grim Trigger is if you defect, we're never coming back. Whereas with tit for tat, you do whatever the opponent did last time. So it's possible to revive cooperation from competition. Here it's not. So let's see that by way of example in the Prisoner's Dilemma. Remember, a Prisoner's Dilemma, we've got two choices. We've got cooperate and defect. In the one-shot game, defecting is a dominant strategy resulting in an inefficient equilibrium. In the repeated game, defecting gets you an immediate gain from cooperation, but it's going to cost you because in the case of Grim Trigger, you're never cooperating again. Because you can never cooperate again under Grim Trigger conditions, there's no incentive ever to deviate, given the right math. And again, we're not talking about discount factors in this game, but given the right math. Now, the reason we talk about this discount factor in conceptual terms is because money now is more important than money later. Payoff now, immediate return now, is more important than immediate return later. We can think of financial reasons why this is the case, in terms of interest rate and so on and so forth. We can think of psychological reasons why this is the case, in terms of patience and impatience. But if someone is incredibly impatient, maybe they want to defect anyway. So what's this a picture of?
Nuclear.
Yeah, it's a mushroom cloud. This is a nuclear explosion. Mutually assured destruction, or MAD, is basically an extreme version of the Grim Trigger strategy. Mutually assured destruction is a military doctrine where if you launch nuclear weapons at us, we will fire them right back at you. Based on the theory of deterrence, right? This is a Grim Trigger. If you launch nuclear weapons at us, they are automatically firing back at you. The entire world will be destroyed. Everyone loses. There are a lot of problems wrong with this approach to international relations. One, maybe we want the planet to survive even if we as a country don't. Two, there are some theoretical problems with it. But in the sense of game theory, where we have abstracted all that away, where we have abstracted from reality, we might think of mutually assured destruction as a grim trigger strategy. And conditional on nuclear armament, where you have missiles pointed at me and I have missiles pointed at you, engaging in MAD, engaging in a sense of mutually assured destruction, is, depending on how you formulate the game, sub-game perfect. You have no incentive to fire your weapons, because you know you're getting bombed right back. You also have no incentive to disarm, which, as we mentioned before, is problematic. Questions so far? All right, so I think that's about it. Let's go ahead and call it. Have a great weekend. Like I said, we are done with game theory in the sense of theory, and now we can start talking about applications and also critiques. Like, why might this not be a good way to think about the world? Next week is interesting because we don't have Wednesday class. We only have that Monday. Remember, slides are online. So if there was anything where you weren't able to take notes, you can just grab those slides from Canvas. Have a great weekend, everyone.